Hey, ooh, sorry. So, can everyone hear me? Do I need to be louder, deeper? Can everyone see me? Everyone? All right, cool. So, welcome. Thank you all for coming. I think I had the longest title in the conference, so you guys, but it'll be fun, I swear. So, are you guys having an awesome day until now? Hands up, who's having an awesome day? All right, that's not everyone. All right, I'll work on it. So, I'm Mircea. I'm a developer working for Google in Munich, and I came here today to show you some kind of cool machine learning developments that a team at Google published earlier this year, and have fun while doing it. I did not actually develop these things, but I'm kind of working with it, and I found them interesting enough to share with everyone. So let's start by showing you this cool app I made over last weekend. It looks like this, and the problem it solves, it's a pretty big problem. A lot of children have this at school, is you get 5 words, like say cat, dog, airplane. This is hard. Bird, giraffe, right? And it's got to say which one doesn't fit. So who thinks it's airplane? Come on. You got to get more active here. All right, let's see who thinks my app is going to get it right. There we go. Nice. So it knows, see it's red. I don't know if you see that, nice, but it's also bold. So that's cool. Let's see what else it can do. Maybe chemistry, oxygen, gold, argon, helium, and hydrogen. So gold is the only non-gas here. All right, let's try a trickier one. Some geography in there. Let's see. Washington. Yeah, that's bad. I'll just put this down for a second. Berlin, Paris, London. So which one's here? Anyone knows? Washington is the only one not in Europe. So that's pretty cool. Let's try some pop culture. And all right, who doesn't fit here? It's the Beatles, of course. Everything else is metal. All right, pretty impressive. So you might think there's some sort of magical knowledge graph behind all of this, or we worked 5 months on developing this, but actually this was all done based on one text file. And we're going to kind of look at how that works. So let's get to slides. There's going to be some numbers. Don't be afraid, but before we get to numbers. So let's look at the problem again. We have 5 words. We got to find the odd one out. Now, immediately, we're going to try to make it a simpler problem. Like, let's say we had some sort of function that told us how similar 2 words are. Right? Just if 2 words are kind of close in meaning to each other. Then we can do it for all. We can kind of run it on all the pairs and find the word that's furthest from the other 4. Right? So we look like this. We're looking for this thing. And we want a similarity, and we want it to be higher between cat and bird than between cat and airplane. Right? So this is a bit simpler. I don't know. We only have 2 words now instead of 5. But it still seems like magic, right? I don't know. How would this work? So at this point, we got to think a bit. What does similarity mean? Like when we say 2 things are similar, 2 people are similar, we usually think about features. We call them features. Like say both people have blue eyes, or they're both tall, or one is tall, one is short, or personality features too. But generally we think about features. So if we had a set of things that are interesting about words, for example, is it big? Is it heavy? Is it an animal? Does it fly? And we give each word a little score on each of these. Right? We'd have a list like this. And we kind of see here, cat is small, light, very much an animal, doesn't fly. We got a -1, so these numbers are between -1 and 1, right? And it's a feline. A bird is even smaller, lighter, still an animal. It does fly, and it's not a feline at all. And the airplane, you can kind of figure it out for itself. What's interesting here is the 0, because we can't really tell whether an airplane is a feline or not. It doesn't even apply to the concept, right? So if we had this magical list of words, then the problem becomes easy, list of numbers, sorry, which people call vectors. The problem becomes a bit easier because we know how to tell how far apart two lists of numbers are, right? Mathematicians call this a dot product, but it's actually very easy. Don't be afraid of it. You go column by column, right? And you multiply things, and then you add everything up. And why this works is because where things are pointing in the same way, they're both negative, they'll be positive and add to the similarity, and where they're pointing in opposite directions, they'll subtract from it. So we see this between cat and bird, we get like minus 0.6, which is a number, it's interesting. But now if we replace bird with airplane, we get a much smaller number. And that's awesome. That's exactly what we want, right? And we can see here why, because a cat doesn't fly while an airplane does. That's a -1 right there. This whole big weight and size difference that contributes. So that's cool. And this list of numbers, this is actually how the app I just showed you works. That's all it has. It's just a map from words to lists of numbers. And you can show it. So let's see, cat. It has like it has 200 of these numbers, but still. And you can see kind of the positive ones are green, the negative ones are red, and the ones that are kind of close to 0 are grayed out. So, actually they're white on on your screen. So if we replace, for example, if we kind of look at feline instead of cat, which is a very similar concept, you might, there's other numbers, but if you look carefully, for example, the 0.27 here, it is identical in both cases. Cat, feline. All right, so that's what it is. When you put something very different, it's very hard to find an airplane. A similarity. Right, so this is cool. This is kind of, we got from words, from concepts, from Slipknot to a list of numbers. But the question still remains. I mean, how did I come up with this? Did I like take a dictionary and put every word, think about every word? Is this a cat? Is this no? We want to do this automatically, right? And right. This is the step. I actually have a clicker. This is the point where we got to look at our data, and we got to make assumptions. And those are two important things people do all the time when trying to come up with these algorithms. And one assumption I can make is I'm going to say words that appear next to each other, like in sentences or in text, generally are more similar. I don't know if that's true, but it sounds kind of intuitive, right? We can kind of work with it. So what we can try to do is start with the words randomly sprayed out. Like that's as random as I could get them. And we go through our text, and whenever we see two words next to each other, we move them a bit closer together. All right, so let's see how this works. My cat is happy, and boo. Now it's much better. No, it's not actually, because they're still a bit random. But next we go on, and we see my bird is happy. And now we move bird and happy closer together. And a very interesting thing happened. Because we moved both closer to happy, now cat and bird are closer too. And if we keep doing this, my dog is happy, dog comes in there too, right? We can also switch up the context. You say my dog is excited, and we get even closer. Now you might notice there's something happening here, which is everything is kind of bundling up together. And if we kept doing this forever, then there was just one big ball of words. So we got to make another assumption. And I'm going to say that random words are actually they're not similar. It's a very low chance that something random, like, I don't know, repaired, doesn't work. You wouldn't find this. So what we can do is we can pick some random words and move them away from each other this time. All right, so we say dog repaired, poof. And dog actually coincidentally, because I made these points, got pushed into the group of animals there. Well, later on, when we go through the text, we see my airplane is repaired, it'll pull airplane away. So you can see just like, I don't know how many, 5 sentences, carefully picked. But we got some pretty nice looking clusters there. We got the animals, we got the emotions, we got the mechanical things. So how do we do this now? We have a new problem. Because I just moved dots on a page, but I was talking about lists of 200 numbers. So how do you move lists together? This might not be intuitive to anyone. So let's think about what happens if we add these things up. We have the cat vector, we have the bird vector, and we add them up. What happens is places where they're similar get reinforced, they get stronger. So for example, the fact that they're both small starts getting a lot more importance. Places where they're different, they cancel out. So the difference is, like for example, we got the flying thing, but they both add up to 0. So what we can try to do is, when we see two words next to each other, we just add a little bit of the other one to each other. I don't know if that's a bit too complicated. I'll show a little snippet of code. There we go. Oh, sorry. Right. So first, we figure out how wrong are we. It's the error. Ideally, we want it to be 1, assuming similarity is between 0 and 1. And because we saw with the dots, the further away they are, the closer we move them together when we move them. And if they're already pretty close, we don't need to do much of a change. And then we add, so the new values for each word will be its old value plus the other one plus a little bit of the other one. And rate, there's a very small number, like 0.05. We want this to be small because we don't want to make big changes to shift everything around. We want this to be incremental. And that's kind of all there is. Like, we can put it all together. We go through we say we have a big text. We go through each word, and we pick every word around it, and we move them closer. And this is not enough, because actually this will cheat. This will bundle together. So we need to do the random word trick too, right? Take 25 random words, push them away from each other. And this is actually all the algorithm and how the app works. Now you're probably thinking 3 things. 1 is, this is bullshit. 2 is, I don't have time to implement this by myself. And 3 is probably, okay, this might work, but I need like 50 petabytes of data and like a supercluster to run thing for 3 months, right? And I'm going to try to prove to you that that's not true, live, by making the app work in Czech instead of English. Ooh. All right, so demo time. This will be hard. All right, so what do we need? Let's get a machine to run things on. I'm gonna use compute engine because it's convenient. I'm gonna get a new instance. Advanced options. Call it Word Worker. I'm gonna pick the beefiest thing we got. Single machine, 16 CPUs. That's pretty beefy. And I have prepared an image there. But all it has is like developer tools pre-installed, so we don't have to get Make and Vim and stuff like this. And because at some point we want to communicate with the App Engine app that I just showed you, we're going to give it full storage access. So let's go. How this works? Creating a computer. Any minute now. All right, cool. So now we have this cool SSH button. All right, so now we have the computer kind of, it's starting up. What do we need? Yeah, the code. Forgot about that. So the team at Google who did this research earlier in like February, they actually were nice enough to open source it on Google Code. It's called Word2Vec. And it's a C implementation. It's super simple. So we're going to see how to use it today. This is the page. I'll have links at the end. But so let's check it out. Actually, no. Wait up. Let's make a work directory. All right, let's check it out now. And I know February is old news, but I just found out about this and it's pretty exciting. Okay, good. So we see there's not actually a lot of files, and most of it is in this one C file. The other stuff is just for demos. Let's build it. Ooh. So this is stuff I had pre-installed, Make and stuff, Subversion. Okay, now it's built. We have this cool binary there. So it's cool. We have the tool, we have the computer. All we need is the data. Now, where can we get a whole bunch of Czech text? Anyone know? Any idea? Exactly, Wikipedia. Did you see I had this opened? Here. so ideally, we would use the latest Wikipedia, but just for fun, I'm going to use one from 10 years ago because it only has 60 megabytes, and I have to do this live. So let's do a copy. It will work with the news one. So let's copy it. Did I close the SSH? I think I did. No. What? Sorry, demo problems. No. No. All right. I don't know where it is. Oh, here it is. Okay, so cool. So let's get it. What do you get? That's the link we just copied, and we can see the Google servers have pretty good downlinks. 5 megabytes per second, and it's going down or something. Hopefully this works. I don't know. I never tried this live. Oh, and also the app is public, but please don't go there yet, or you'll run me out of free quota. But you can go after I'm done, especially when it'll be in check. All right, so we're done. B unzip. Unzip it. And now comes the part where I worked the most for this, which is I had to find a Perl script that cleans up the Wikipedia. Because if you look at it, it looks like this. Ugh, not words and sentences, tags and stuff. So here's this Perl script that I found. And I'll tell you all about it while it runs. Clean up. Clean. All right, this will take 2 minutes to run. Now, the person who made the Perl script I found never thought about UTF-8 in their lives. Actually, the people who made Perl never thought about UTF-8. And the Czech Wikipedia has a lot of weird characters. So it took me 4 hours to make this work. In the meanwhile, let me show you another thing the app does, which is this. It's another problem. You might be familiar. A is to B is C is to D. Right? So let's try this geography knowledge again. Germany is to Berlin. France is to Paris and other big cities in Paris. All right? How does this work? You don't have an idea? I showed you earlier how when we add things together, the differences cancel out, and we just have the similarities. And when we subtract these lists, the similarities cancel. We have the difference between Germany and Berlin, which is being capital. And when we add this back to France, it kind of magically points to Paris. It's pretty cool, and it's actually pretty powerful. Like you wouldn't think, I don't know, let's try this. Hamburger is to meat. Cheese is to milk, right? Because it's hamburgers made out of meat, cheese made out of milk. It even knows grammar. B is to was, can, is to could. So this is much smarter than most fifth graders. Let's see how the Perl script is doing. Still going. All right. I think it does. Let's try this. Let's see if it has like a moral sense. Bad is to good. Ugly. Night? You want to night? Well, morning is kind of in there. But what I was going for was ugly. You know, this is much more impressive. But I'll let it run after the presentation, and you'll feel free to play with it yourselves. All right, good. Now it's done. Now let's look at the wiki. So, whoa, stop. All right, so you guys probably understand that. I have no idea. But what it did is basically removed all the special characters, and it replaced the numbers with them spelled out. Okay, so now, I'm going to put the mic down for a second and type a long command to trigger this learning. This is the binary we just built, and we're going to say train on the main wiki output in size. This is the size of the list of numbers we just used, so we're going to use 202. Window is how far next to each word we're going to look for matches. I was going to say 8. Negative. the number of random words we're going to push things away from. Right, so, okay. I also put 16 threads in there because we got a beefy thing. We're going to run for 15 iterations, and we want binary output. Okay, so it started. It's doing 70,000 words per thread per second. I don't know what that means, but it sounds like a large number. So it might take a while. So let's go back to presentation while this is baking in there. And I'm going to show you some other cool stuff that, that people are doing with this. So we talked about, we use the English Wikipedia, we use the Czech Wikipedia. Now, what do you guys think would happen if we put them both in at the same time? Exactly. Oh man, you're good. I wish I had things to give away. Exactly. We get translations. We use that A is to B thing, and because the words are both kind of similar words are grouped next to each other in each language, once we know the translation for one word, we can find out the translation for others. Now we can go even further. We've been talking about words, but there's nothing in here that says these have to be, words in any language. For example, we can use images and words and put them in the same thing together. And people did this, and apparently they took like Wikipedia images and their captions as the context. And apparently, images get kind of clustered together with the words that they describe. So you can have some sort of like very basic. Now, the bad thing about this is it doesn't deal well with new images that it hasn't seen before. So, not perfect, but working on it. And there don't have to be words in there at all. In fact, Spotify ran this with using songs in their playlists, and they came up with a pretty good song and author similarity measure, right? You can read the things. Yeah. But most importantly, you can think about your data. I don't know what, your startups, whatever. Just kind of look at your databases. Look, if you have any sort of things that are in a sequence, you can start considering, hey, do I want to know if these things are similar? So, for example, items in a shopping cart or users themselves. They have properties, they have cool stuff. Go out, look at stuff. Now let's see if this is done. If it's not. 42%. Oh man, we're gonna have to spend 3 minutes doing cool stuff here. So, does anyone have more ideas to throw at this? It's now or never, because it's in English. Once it's in Czech, I don't guarantee anything, except the words I explicitly tried. Let me think. Oh yeah, let's try see with the bands. But let's try replacing Slayer here with Banana. Now kind of, Banana's the odd one out, because Beatles are still making music, even though they're not metal. Let's try some more. 54%, all right. And we can cheer it on. I had it run for, so because we have so little data, it's just 60 megabytes, right? I had it run for 15 times over the same file over and over, because else we're not gonna get pretty good quality. So it might take a while. But this is to go to show you, if this works with data from 10 years ago, imagine what you can do with not 6 minutes of training and a full thing. Okay. This used to be faster when I practiced. Let's see, what else do we have here? Oh, okay, I can show some more stuff. I played with, let's try Volkswagen S2, Passat, Skoda, LB, Fabian. Pretty cool. What's the second word? All right, so it's not. What else is there? Yeah, this is the classic one they always use. Is woman is the queen. Man. King, Lord, no, kingly. We also get some pretty good synonyms out of this, surprisingly. Yeah. Oh, yeah, I kind of like it. That's good. Dog. It fits. or monkey, but it's come on, 79%. Come on. I wish I could just stop it now and like because you know it's pretty good already. I would say, but I don't know. I should have picked the smaller numbers. It'll be exciting at the end, I swear. I promise. But I'm gonna need some help because I don't know Czech. So how do you say cat? Kočka? How do you type that? Oh man, all right. Actually, let's prepare this. Cat in Czech. Yeah, good. Actually, I wonder if this works. I'm gonna put all of them in. Cat, dog, bird. What do we have? Airplane. Is everything correct there? Yeah. All right, cool. I'm ready here. Come on. Go for it, 94%. All right, cheer it on. If you believe in it, it goes faster. For sure. But at least nothing failed until now, so that's surprising. I had 3 backups. Well, still time to fail. 98. 9. Come on, come on, clap. Oh, come on. Oh no, it's done. It's done. All right, good. Woo! Thanks. Wait up. So let's copy it into the app. It was an App Engine app, and there it loads things out of cloud storage. So let's do that. So Google Storage Util copy. What was it? That's the bucket name I chose. Copying over. Let's see how big it is. This is usually fast. All right. So it's 131 megabytes for the big hash table from words to numbers. And that's actually how big the English model I just showed is too. Right? So we can encode so much meaning into kind of little data. This could be on a phone or on a robot. No. Actually, don't put it on a robot. I don't know what happens. And in the meanwhile, let's prepare the app. So the app is using, it's Python, and it's using a port of the C implementation by a developer from Prague, actually. So all we have to do is read the file here, old Czech model, open it with GCS, and we pass it into this Python implementation to read up. And the rest of the app just calls convenient methods like model.doesn't-match. So that's impressive. Let's update the app in the meanwhile. Oh, I got the cheats here. I had them all pre-made. So the app updated. See what, or maybe yes. See what the file is doing. Copy it over. So now, if everything works correctly, we need to refresh. And oh, let's go for the words. Go for it. Ooh. Really? Why didn't you say that before, man? Where? Old?
You call it model here, but you uploaded as a week.
Did I? No, I didn't. Okay. So, let's see. I up old check wiki. Oh man, you're right. Oh damn it, you caught me. All right. No, it's overrated. I want to be fair. Should have said so before though. No points for that. Maybe it's going faster. But yeah, I actually prepared this before, so. If you don't believe. I had the file already there. I just didn't overwrite it this time. But I'm not a cheater. I'm going to show you. Cheated by mistake. It's not my fault. All right. Let's try it now. Okay, so now you saw me overwrite it. Oh, man. Even going to put them in a different order. Boom. No, this actually works, I promise. There's nothing fake about it, unfortunately. And you know, we put the Czech wiki in there, so it must know a whole bunch of things about you know, Czech things now. So let's try this. It's like, let's see. I know Prague, and I know city. How do you read that? Mesto? Miesto. Okay, good. And I know Vltava. So hopefully. Is anyone down the river? Yeah. So that's the translation thing we're talking about, except, you know, I just did it by hand. So now the app is free. Go for it. Kill it with fire. You'll run at some point I'll run out of quota, but it's actually everything I had. So, you know, questions. Go for questions. Come on, don't be shy. Go. Slight simplification. Actually, so conceptually, it works exactly like that, except people put a bunch of optimizations in there to make it run faster. But I didn't write it. I didn't write it. Actually, Jeff Dean, a team of Jeff Deans, if you heard of him, they wrote it. But yeah, they did no library. I mean, you can see. Maybe I can show it. It's kind of ugly, but the whole code is like 400 lines of C, and you can read it. Where is it? Where to? All right, kind of looks like this. Yeah, there's a lot of reading and stuff, but there's no libraries. So there we go. And there's no neural networks. I mean, sure, you can consider this a neural network, but the main point is, you know, machine learning is not something. It doesn't have to be difficult or esoteric, or, you know, you need a whole bunch of stuff to use it. It can just be, we have data and let's see what we can make out of it. Right? Other questions? I'm going to do that. Go ahead. Exactly, yeah. So when we do the A to B thing, we find where we got to go, and then we pick the closest word to that, or the closest three. So the question is, if we have both words and pictures, do we need to do any special things? Mm-hmm. Yeah, that's a different thing. That works on new pictures and it's nicer, but it's more complicated. I mean, you might have seen this. So recently, the same team published a thing where they kind of identify objects in pictures. And this what I just showed you is actually used in there. but only on the output. So when they produce the sentence that is, a dog chasing a frisbee, they use these vectors to find out kind of what is a dog, what is a frisbee, and stuff like that. Yep, cool. Other questions? Yeah, actually, if you're not afraid of math, oh, sorry, let me give you the links here. This stuff. Or were you referring to the image algorithm? To the images? Oh, yeah. So yeah, this is the problem where, for that, you kind of need a lot of computers and data. But they published a paper on it. You can read it. But if you're interested in more, you can find out, read these references here on the page. Yeah, that's the link to the Python port. If you have more questions, you catch me an email or at the after party. And I'm going to put the code for the app and everything I just showed you on GitHub, but I didn't get to yet, so later today or something. Yeah, check me out. Cool, that's it. Done.